Hello, everyone. Welcome back to CMPT 456 Information Retrieval and Web Search. This is the part 3 of Information Retrieval Models. In the first two parts, we introduced the basic idea about information retrieval models and discussed the Boolean model and the probabilistic model. In this part, we'll continue the discussion and introduce the language models. For a query queue, one intuitive idea for a search engine to rank the documents is to compute something like the probability of D given Q, where D is a document and Q is a query. And here, the intuitive idea behind this probability is that given that Q represents the information need, what's the probability of D may be the representation? To be more mathematical, we can understand the probability of P, D conditional on Q as the probability that a document D may be generated using the same mechanism that generates the query Q. We'll give the formal definition of P, D conditional on Q and how to calculate this probability later. But at this time, one thing we can do is that we can use the base rule to rewrite this P, D conditional on Q as PQ conditional on D times PD divided by PQ. Now, we can easily see one thing is that for query Q, because once Q is given, the probability of Q is the same for all the documents. PQ indeed is the probability that a user may ask question Q. And for PD here, PD can be assumed the same for all documents in a large document collection, or can be set as the weight based on the authority or quality of the document. Essentially, PD is the probability that a user may find document D relevant, useful, given all kinds of queries. Then the question becomes how we can estimate these P, Q conditional on D. This leads to the idea of language models. Here, in language model, we treat a document as an instance of a generative model. If you are not familiar with generative model, essentially a generative model randomly generates observed data, such as words in a document. Typically, a generative model takes some hidden parameters to decide the mechanism to produce such data items, such as the keywords in a document. We'll give an example to illustrate how the generative model will generate a document, or indeed the set of words in a document. And in such a way, the model can also generate some other documents according to the same probability distribution. Then, under this assumption, for a query Q and a document D, the probability of DQ conditional on D is the probability that the query Q is generated by the same model which also generates D. And here, so-called model is a probability distribution of words, and the mechanism of generating a document or a query is to draw a random sample according to this distribution. As we can see, the larger the probability of Q conditional on D, the more relevant Q is, with D. There are some other options of language models available. We'll discuss some of them later at the end of this part. So a language model essentially is that for each document D, we try to learn a model MD that will generate the documents similar to D. Let's start from the simplest language model, the unigram model. A unigram model follows a probability distribution over all the words in the language. Here, each word or each term is associated with a probability. Then, in this way, we can draw a distribution, a sample over the vocabulary, and if the sample happens to be the same as the words in a document, and then we say the model generates the document. In order to do this unigram model, indeed, we make an assumption is that the previous word should have no impact on the next. In other words, we assume that a document is a set of words, and those words happened independently. Of course, this is an assumption oversimplifies the situation. It is far from true in practice because when we write sentences, of course, the previous word has some effect on the next word we will use. But it happens that the unigram model indeed works pretty well in practice. And then for all the words S in the alphabet, and the probability of these S altogether, the sum of those probabilities should be 1, which is the articles generated by the unigram model. And to that extent, we can regard a unigram model as an automaton of only one state, which is itself. And we have an explicit stop probability is needed in theory, but is often omitted in practice. Well, the unigram model has been shown very effective in practice. In this case, for example, this is the automaton of the unigram model. We have only one state Q1 here, and then we have a loop from Q1 to itself. For example, we have a sentence say, frog said that Todd lies frog. And then we have a distribution of probability on those words. And each one is associated with a probability here. And then the probability that this model will generate this sentence is the product of all the associated probability, because we assume that those words are independent from each other. And you can see here, we also have the 0.8 here, meaning at any time, Q1 has a probability of 80% to continue to the next word and has a probability of 20% to stop. So that's the reason we have this 0.8 here, and we also have the 0.2 at the end of the sequence. We realize that indeed the unigram model is far from the real situations because it assumes that all the words in the document are independent from each other. Can we model the relationship or the dependence of a word between a word and the words go before current word. Yes, this is the idea of n-gram model. Essentially, what we need to do is that we use the previous n minus words to predict the next word. And if we set n equals 2, then we have the bigram. Bigram essentially lets us to guess the next word based on the previous word. So this is the n-gram model, and it shows some minor improvement on the unigram model, but it also incurs a lot of processing cost. Now, from words, let's think about a topic. Indeed, a topic can be regarded as a probability distribution over many words. For example, if a document is about COVID-19, then there are several terms related to COVID-19, the symptoms, the treatments, and the spreading means may also appear in the document. If a document is talking about hiking in Vancouver area, then the words associated with hiking and the locations in Vancouver, such as Squamish, may be as expected with higher probability. Therefore, we can use the distribution of some certain words to represent a topic. Then, a topic model contains probabilities for all the words. Most of the words will have the default probabilities that are the same for any text, but some words highlighting the topic will have substantially higher probability or substantially distinguishing probability. The language models cannot generate the original document by the model. Please pay good attention to this, because the models about the word distributions, there's no structure is considered in the language model. Now, we can do the multinomial distribution. At any given time, there are omega, absolute value of omega, that many possible words that can be pulled out for a document D. Here, omega is the vocabulary of our document collection. We cannot describe the text burstness, because a word, in reality, when we write an article, if a word is being pulled out, then it tends to be pulled out again and again. So then, for a document D of length LD, we can calculate the LD equals to the term frequency of term Ti in D with probability I equals 1 to omega. And then the probability of this D can be computed in this way, where the factorial of LD is a constant for all language model generating this D. Here, because we get D, and then in this document D, we can get for each term the frequency. Therefore, the sum of the term frequency in this document indeed will produce the length of the document. We can build the language models for both the queries and the document. And therefore, because we have query, we have documents, so we can build the query model, we can build a document model. We can use those language models in many different ways. First, we can what you can do is that we can compare the models use the query model to check what's the probability that the query model may generate a document or we can use the document language model to calculate what's the probability of the document model may generate the query. We may also compare the query model and the document model as two distributions. So those different ways are used by search engines to produce the rankings of documents against one specific query. Now, we are facing one question: how we can estimate the probability distribution? How we can estimate what's the probability of a document? Given a query queue, suppose queue contains multiple terms, say Q1, Q2, until Qk, where k is typically a small number. Then the probability of a query queue conditional on a document D can be calculated in the way like this. Here we assume all the terms in a query are independent. Therefore, it is the product of the probability of this queue belongs to this query conditional on the document model. For query term Q, the maximal likelihood estimate of this probability Q conditional on D is indeed what's the term frequency of Q in this document D normalized by the size of document. Well, this calculation is pretty straightforward, but it may have some problems. First, if a Q does not appear in this document D, and then, according to D's estimation, the probability of Q conditional on D would be 0. And once you have a 0 here, because the probability of Q, the query conditional on the document D, is the product of those term probabilities. And if one term has a probability 0, then the overall product will be 0. Then that defeats our whole purpose. And also, to some extent, the language model of a query should be somewhat different from the document D itself. Even the term Squamish is not mentioned in the document about hiking in Vancouver. The probability of Squamish in a document D related to hiking should not be absolute 0, because the documents is short comparing to the whole vocabulary, the whole alphabet. Therefore, a document D may not be able to contain all the related works. We need to do some technical treatment to make sure that we can overcome those shortcomings to make the document model more powerful in matching a query queue. This is the idea of smoothing. The idea of smoothing is that we discount the probability estimates for the words in the document and assign some leftover probability to the estimates of the words not in the document. To do this, indeed, we set a parameter alpha, which is a very small portion. What we can do is that the probability of Q conditional on D is 1 minus alpha times the probability of Q conditional on D. This is what the probability you observe in the document D, and plus the alpha times the probability of Q conditional on C, which C is a large collection of the documents. Therefore, we use a large collection to estimate the probability of a term Q appears, and then use these to avoid the problem that the query term Q does not appear in the document D. And there are some other methods like this Janick-Mercer method. Essentially, it used the CF collection frequency of Q in a large collection to as this PQC. The smaller the value of lambda, the same of alpha here, and then the less smoothing. And extremely, when this lambda equals 0, meaning this is a Boolean search. That means Boolean search only finds all those documents exactly matching the query. If a query term is missing in a document, Boolean search will not return the document. Another way to do this is that we can make a pseudo document or pseudo counts. Essentially is that we can compensate a document by attaching some virtual part of the document representing the possible distribution. Technically, for document D, we can view the document language model MD as counting the actual words from D, which we can observe, and the pseudo counts of words in a pseudo document of length mu. The probability distribution in the pseudo document will follow the same distribution in the whole collection so that we can avoid the situation that query term Q does not appear in a specific document because it still will be smoothed by the pseudo document. A specific way to do this smoothing is the Dirichlet smoothing. In this way, we can have this formula here, and then we set the alpha equals mu divided by the length of document plus mu, and then we update the probability of query term Q conditional on D using this formula. And the smaller the value of mu gives more weight to the matched words, and therefore the less effect of smoothing, the same as we discussed before. And typically, the Dirichlet smoothing is more effective than the Janick-Mercer smoothing, especially for those shorter queries. Now, we discussed the document likelihood model. The idea here is that we look at the probability D conditional on Q, which is the probability of generating a document D by the language model of query Q. Then, because the query text is typically very short, a query typically contains only a small number of words, then much less text will be available to estimate a language model based on the query text. In order to estimate the query language model, one thing we can do is that we can incorporate the relevance feedback such as pseudo-relevance feedback to enrich the information associated with the query so that we can still get the query language model. Another way is to make a model comparison. We can compare the language model of the document and the language model of the query. And if the two models are similar, then likely the query document is related to the query. And if the two models are very far away, then the document and the query may not be relevant. How can we compare two probability distribution? We can use the KL divergence, which is a popularly used measure between distributions. KL divergence is also called the information divergence, the information gain, or relative entropy. KL divergence is calculated in this formula. We can use the distribution Q to represent the distribution of P. And then KL divergence essentially calculates what the information needed to make this representation. So it takes the px divided by qx, the log value, times the probability of x, and we sum up all the possible values of x. Here we make a rule is that if px is 0, and then this log will be 0 times log 0 will be 0. And in such a way, we can calculate the KL divergence of MD given MQ in this formula. There are several properties of the KL divergence. First, KL divergence is always positive. And the larger of KL divergence, the less similar the two distributions. The more further away the two distributions are. And KL divergence is not symmetric, meaning if we switch the position of P and Q, we will get different results. The KL divergence of P based on Q is different from the KL divergence of Q based on P. That is the reason, that's due to the reason which distribution we will use as the base. And also, KL divergence is not a metric, meaning it does not satisfy the triangle equality. If we have three distributions P, Q, and R, the probability of P given Q may not be smaller than the KL divergence of, say, P to R and then R to Q. And in many cases, we would like to use the query language model as the true distribution and use the document language model as the approximation. So typically, we will do in this way. And if we use in this way, and indeed, you can see the query likelihood model, it becomes a special case. And also, we can extend it, the probabilistic model to n-gram probability. Here, the assumption is that the probability that pulling a word T in the document should depend on the n query words we have just pulled out. Therefore, we will have the formula in this way. The probability of T given Q is approximated by T given W1 to Wn, which is the probability of T W1 to Wn over the probability of W1 to Wn. Okay. Given the language model, we can make the ranking in a two-pass method. In the first pass, we rank documents using the query likelihood to obtain the weights needed for the query language model estimation. And we can use the pseudo-relevance feedback process. In the second pass, we can then use the KL divergence to compute those similarity and then rank documents according to the similarity. Because we want to compare the similarity between the queries and the document, therefore we use the query language model as the true distribution and vary on the document language model. So the detailed steps are as follows. We first rank documents using the query likely score for those query Q, and then we select some number of the top ranked documents, and typically these may be between 10 to 50 of the top ranked documents, and we calculate the query language model probabilities. Then Accordingly, the document language model probabilities can be estimated using, for example, the Dirichlet smoothing. And then we rank the documents using the KL divergence scores. And typically, again, we only use a small number of high is probability words to estimate this ranking. In summary, we compare the models in the following way. We're using the KL divergence as a generalization of query likelihood scoring. And then, the more accurate queries that reflect the relative importance of the words in the topic. And we may use the pseudo-relevance feedback based on the formal framework of the language models. This wraps up the whole section on information retrieval models. And the important thing here is that we introduce the probabilistic ranking principles and the binary independence model. And then we talk about the ranking in the BIM. For example, using the pseudo-relevance feedback iteratively. We also talk about language models. The queries and the documents are generated by some models. And we talk about how to generate such models, how to learn those models from data. And then we focus on the unigram model and also mention the idea of n-gram models. And we discuss how to use the language models. We can use the query likelihood and document language models, or use the query language models. And then we may model similarity between two different language models using the KL divergence. Then we can do the ranking based on the language models. That's all for this section. Thank you and bye-bye.